In our last video, we talked about how to use the message passing interface library to do some parallel calculations without actually any kind of inter-process communication, right? And every core was just reading its own input file, doing a summation for all the numbers listed in its own input file, and then writing out its own output file. And and it's basically just every core just doing its own thing. It's not really communicating with every other core. So in this particular lesson, we are gonna talk a little bit about some collective communications. In particular, we're gonna talk about a broadcast communication and then a reduction communication. And we're gonna use a specific example, which is called the area under a curve. So the problem that we're gonna try to solve is basically doing a numerical integration of a curve. So a integration is basically a summation. So we're going to use a Riemann sum, to approximate the integral of a curve. So how do we actually do this Riemann sum, right? We basically just draw rectangles. We're just going to draw rectangles, and we're going to use a left-hand side Riemann sum. Basically, the value of each of the rectangle. So rectangle has a height, right? The height of a rectangle is determined by the value of the function uh, on the left side of the rectangle, right? It's gonna be the left side of the rectangle, right? And then we're gonna approximate the area under the curve by calculating the area of each of the rectangle and then do a summation of all those rectangles. So if you imagine that we have lots of those kind of rectangles, lots of those rectangles, many of them. So each one of them will be really thin. And if we can actually compute the area of each of the rectangle by multiplying the height with its width, and then do a summation of the areas of all the rectangles, we will be able to get a very good approximation for the area on the curve, under the curve, right? So the accuracy will be dependent upon how many rectangles we're gonna have. Right? If we have lots of rectangles, each rectangle will be really thin and tall, right? Each one of them will be really thin, and then we are gonna get a very accurate approximation to the area under the curve. But if we have just a few rectangles, like what's showing in this particular figure, and then the approximation won't be very good, right? So that's our uh, that's our problem. That's our mathematical problem. This kind of mathematical problem has lots of applications, not just in math, but also in many different areas, in science, in social science, in economics, in chemistry. Lots of kind of applications actually are going to use this kind of numerical integration technique. And um, lots of this kind of numerical integration software already exists on the market. You can actually just do that, for example, in MATLAB, right? But most of those software are actually sequential, so they are just going to use like a single core or a single thread or a single process. But we're going to write a parallel program. We're going to write a parallel program using the message passing interface and do this kind of calculation in parallel to speed up the entire calculation, basically, by using MPI. So before we actually try to solve this particular problem, let's think about it. Let's think about how we can actually write this particular program, right? So what might be a good starting point for us to actually start to actually write a program to solve a specific problem, right? Usually, what I would like to do is to actually start with data structures. We need to identify what are the major components, what are the major containers that's going to be used for storing the data that's going to be used in this particular program, right? So let's try to think about what might be a useful representation that we can use to actually represent this program, right? The first step is to identify the data structures that's going to be used for representing this problem, right? So most of the stuff, most of the the components of the problem are actually marked with those letters A, B, C, D, E, F, G, H, I, J, K, all those letters, right? The the first thing, probably the most important thing is actually a representation of the function of the curve, basically the curve, right? We need a representation of the curve. So how do we actually represent a curve, right? We can we can represent it using a function, using a C or C++ function to represent a particular curve, right? So if the function is f equals to x squared, then the function we can actually implement a C or C++ function that's going to take x as the input, and then the output is going to be x squared. So a is actually a function, right? So let's just give it a name. Let's just call it func. Let's just call it func. That's going to be we're going to use the func, this particular function, to represent our curve, right? And then the second thing is that we're going to have lots of those rectangles, right? We're going to have lots of those rectangles, but we need a count of how many rectangles we're going to have. So b is the total number of rectangles. So we're just going to introduce a variable, which is basically an integer. That's n rectangles. That's how many rectangles we're going to have. That's how many rectangles we're going to have, right? And then we need a representation of the width of the domain, basically where the function is actually defined, right? In practice, we cannot really do an integral from minus infinity to positive infinity. We are doing an integral for a finite domain, right? A finite interval. So we need a representation of the width of the domain, basically, which could be a floating point number, right? So we're going to use a floating point number, a double precision floating point number, to represent the domain width, and then we're going to call this particular container just the domain width, right? And this domain width can be computed from the left boundary of the domain and also the right boundary of the domain, right? So D is actually the left boundary of the domain. So x left, we're going to call the left boundary x left, which is supposed to be a floating point number, right? So it's going to be a double, in fact. And then you have a right boundary, right? I is going to be the right boundary. Let's call it x right. X right, that's the right boundary of the domain. So the domain width is just x right subtract x left, right? And then once we have a width for the entire domain, and we also have the total number of rectangles within this domain, then we can just compute the width of each of the rectangles, because we are actually using we are assuming that every rectangle is going to have exactly the same width, and the only difference is in terms of the height, right? That's the heights for different rectangles are going to be different, but the width is going to be identical. So E is actually the rectangle width, right? And then we're going to use a variable name that's called rectangle width to represent this particular number, this width, right? And then for each of the rectangle, it's going to have a height. It's going to have a height, and in this particular figure, f is the height of the rectangles. Suppose we are looking at this particular rectangle, right? How do we actually get the rectangle height, right? We basically just taking the left point, the coordinate of its left boundary of this particular rectangle, and then once we have a coordinate, we can actually send that coordinate to the input of the function to compute the value of the function, right? The value of the function basically gives us the height of the rectangle, right? So once we have the height, we're going to call this height my height, right? And my height is going to be different for each of the different rectangles, right? And in order to compute my height, I need a reference to a value for the coordinate of the left boundary of the rectangle, and I'm going to call that coordinate my left, right? And then we also need a index for each of the different rectangles, and then I'm going to call that index I rectangle. So I rectangle is going to go from like 0 to n rectangle subtract 1, right? And because we're actually going to sort of do this kind of calculation on on several cores, we're going to partition the entire problem onto several different cores. So each of the different core is going to compute a summation of parts of the rectangles, just a subset of all the rectangles. Suppose I have like 2 cores for these 6 rectangles. So the first core is going to compute the summation of the first 3 rectangles, and then the second core are going to compute the summation of the areas of the next 3 rectangles, right? And those partial summations are going to be stored in a variable that's called sum local, which is basically a localized sum. It's just a summation of the areas for the rectangles that's on each of the different core, on each of the different ranks, basically, right? And then once I get those sum locals, I can add those sum locals together, and then get a total sum. And that total sum is going to be an approximation to the area under the curve. So that's going to be the primary data structures we're going to use for representing this problem in our computer program. And in order to actually solve this problem, we're going to use some MPI functions. We're going to use 2 MPI functions. One is called a broadcast, right? Broadcast, conceptually, you can think of it like that. Suppose I have like 8 different cores, right? And then each one of them is going to have a rank that's a unique ID, right? Suppose rank 0 actually has computed some data or obtained some data from the user, right? And rank 0 wants to give that data to every other core or every other rank. Then it can do a broadcast, basically send out the information that's holding by rank 0 to every other core or every other rank. That's called a broadcast, because you're sending information from one rank to every other rank. So that's essentially a broadcast. And the MPI library actually implements this kind of a broadcast communication very, very efficiently using some kind of tree structure. So it's not like the rank 0 first sent the information to 1, and then after that information is sent, it sends the information to 2, sends the data to 3, sends the data to 4. It's not doing this kind of sending sequentially. It's not doing that kind of thing. It's actually using some kind of tree structure. It's using a tree structure. So first rank 0 has the data. It sends the data to rank 1, right? As soon as rank 1 receives the data, it has a copy of those data, right? And then rank 1 can start to send data to other ranks also. So rank 1 is going to behave like a helper for rank 0. And then you have both rank 0 and rank 1 starting to send data to every other rank now. So rank 1 is going to send data to rank 3. And at the same time, rank 0 is actually sending data to rank 2, right? So as soon as rank 2 and rank 3 has a copy of the same data, so rank 2 and rank 3 can act as helpers, right? So they start to send data to additional ranks. So rank 3, you can sort of see rank 3 is actually sending the information to rank 7. And at the same time, rank 1 is not idle either. Rank 1 is still working. It's sending data to rank 5. And then at the same time, rank 2 is actually sending data to rank 6, and then rank 0 is actually sending data to rank 4. So it propagates the information in this kind of a tree structure. So it can actually implement this. MPI actually implements this kind of broadcast operation very, very efficiently by using this kind of a tree structure propagation. That's a conceptual diagram, right? That's a conceptual diagram. So how do we actually use this kind of function in our codes, right? How do we use this kind of function? So here is a copy of the user manual. So that's how you can actually use the MPI broadcast. So MPI, that's the namespace scoping your communicator. In our case, it's just a COM word, and then followed by the function, right? The name of the function. That's called bcast. It's not called broadcast. It's called bcast. .bcast. You're invoking the bcast function on the communicator, right? So in this particular example, it's actually broadcasting one integer. That's called myval, right? And then the first input is supposed to be the address of the data buffer, right? So what exactly is an address, right? It's not really like a copy of the variable. It's a handle to the location where you're actually storing the variable. So the first input is not really the variable itself. It must be the address of the variable, right? It's the location in the memory where you store the variable. So that's what's expected for the first input. So how do you actually get the address? It's actually very easy. All you have to do is to write down the name of the variable, that's myval, and then prefix with the ampersand. Prefix it with the ampersand, then it's gonna get the address of that particular variable, and then you just send it to the first input. And then the second input is the count. It's an integer, it's count. It's basically telling the MPI how many numbers I'm going to send. So here it's basically just sending one integer, so all I have to do is to put a 1 here. And then the next is a data type. So what's actually the type of the data that you're actually trying to send, right? So here you're actually sending out an integer. So for some reason, this particular user manual has some typos, I guess. It's not really an MPI double. It's supposed to be an MPI int. But here you can actually find all those different kinds of types that you can use, right? So if you are actually sending out one integer, you are supposed to use MPI : the scoping operator int, right? And all in capital case. It's case sensitive. All have to be in capital case. So you have to sort of replace this MPI double with MPI : int, right? That's the correct syntax. So this seems to be incorrect. And then the last one is very, very important, which is actually the rank from which the data is being sent out, is being broadcast, right? Here it's called a root. It's root. It's actually the first process, the first rank that actually holds the data, right? So all the data are going to be sent out or broadcast from this particular rank. Here we're actually using 0. So 0 rank is going to be used as a broadcast root. So all the data is going to be sent out from the root. That's called broadcast. We're going to look at this broadcast data, how to use the broadcast in solving our area under curve problem, right? And then a second collective communication style is called reduce. So what exactly is a reduce, right? What exactly is a reduce? Conceptually, it looks like that. So rank 0 has a number that's 5. Rank 1 has another number that's 2. Rank 2 has another number that's 7, and then rank 3 has another number that's 4. Suppose I want to add those 4 numbers together, but all those 4 numbers are residing on different ranks, so they are basically in the memory of different computers. So how do I actually collect all those data together and then do a summation, right? And we have a MPI reduction operation. That's called MPI sum. So using this particular operation, you're going to collect all those numbers together and then sum them together and then reduce it to one of those ranks. Here we are actually storing the summation of those 4 numbers onto rank 0. The summation is supposed to be like 18, right? So here we are summing together just the 4 numbers, and each of the rank has just one number, right? Suppose each of the rank has has more than 1 numbers. So rank 0 has like 2 numbers, maybe stored in an array or something. It has 2 numbers, 5 and 1. And then rank 1 also has two numbers, 2 and 3. And then rank 2 also has 2 numbers, 7 and 8. Rank 3 also has 2 numbers, 4 and 2. So if we do a reduction using the MPI sum operator, we are doing a summation. And then we're going to reduce the result back to rank 0, right? What's going to be the result, right? The result is going to be 2 numbers. It's not 1 number. It's actually 2 numbers. So MPI sum, this reduction operation, is going to do what? It's going to do a summation for the first number on each of the rank, which gives you 18. And then that's going to be the first number of the reduction result. The reduction result is going to have a second number also, and then the second number is going to be a summation of the second number on each of the rank. So it's 1 plus 3, that's 4. 4 plus 8, that's 12. 12 plus 2, that's 14. So the reduction is going to be performed element-wise on each of the ranks. So the first element of the reduction result is going to be a summation of the first element on each of the rank, and then the second element of the result is going to be a reduction of the second element on each of the rank, right? So that's the at the conceptual level, that's what a reduction operation actually is. So how do we actually use reduction function uh, in code, right? So here's another copy of from the user manual, right? So MPI, right? That's the namespace, and then common word, that's the communicator. We're calling the reduce function, RUDUC, reduce function on the communicator, right? And then the first input is still the send buff, the data. So it's actually the data that's going to be on each of the different ranks. On each of the different ranks, you're going to have a buffer that's going to be used for sending the data to the reduction operation. Right? That's called a send buff. So here we are actually just using a floating point number, MPI float, basically. And then we're getting the address of my val. That's the value that we're actually trying to reduce. And then the second input is the receive buffer. The receive buffer is what? Is the address of the receive buffer. The address of the receive buffer is basically the location where you want to store the results of the reduction operation, right? So we go back to this particular diagram, right? So the send buff is going to be 5 on rank 0. It's going to be 2 on rank 1. It's going to be 7 on rank 2, and then it's going to be 4 on rank 3, right? So all those different numbers are stored in a variable that's called my val, right? So on rank 0, my val is going to have a value of 5. On rank 1, my val is going to have a value of 2. On rank 2, my val is going to have a value of 7, and then on rank 3, my val is going to have a value of 4. And each of the rank is going to call the reduce function, and the first input is going to be the address of my val. So every rank is going to send out a different value of the my val, right? And then val is going to be the location where we collect the reduction results. So the reduction results on rank 0 is going to be val. That's 18, right? That's the summation. So val is going to have a value of 18 on rank 0, right? And then how many data we're actually sending out from each of the rank, right? For this particular example, we're just sending like one number, and then the type of the number that we're sending out is basically just a float. And then the next interesting thing is the operation we want to apply. Is the operation that we want to apply, right? In this particular example, it's just a summation, right? And then we have an operator. We have a representation of the operator, right? It's called MPI colon sum, all capital case. And in practice, we have a choice of many different kinds of operations, right? We can take the max, we can take the min, we can take the sum, right? We can take the product. It's basically multiplications. We can take the maximum, the location of the maximum, that kind of thing. And then the last parameter is, in this case, it's called int root, right? It's actually the rank we want to reduce the value to. And in this particular example, the rank we want to reduce the value to is basically rank 0, right? So we just put the rank 0 here, 0 rank, it's an integer. And that's how we actually use the reduce function. So now let's look at how we can actually use these two kinds of functions to solve our area under a curve problem. So I'm gonna switch to my terminal. So I'm still inside of the the directory that I created for the last video. So I'm gonna switch to a different directory. I'm gonna create a new directory. I'm gonna call it area under curve, and then I'm gonna switch into that particular directory, right? And now I need to start to write my code. So I'm gonna call my code area.cpp. I'm gonna call it. So I wanna keep my code inside of this particular window that I'm recording. So that's gonna be my editor, right? So the first thing we're gonna do is to actually write the include. So I'm gonna include everything for now. I'm gonna include everything that's defining the headers for the standard libraries, and then I'm gonna include the MPI headers, MPI.h. That's the MPI headers, and then I'm gonna using namespace std. So just save me some typing of the std namespace and then the scoping operator, that kind of thing. So the first thing I'm gonna do is to write the function. I'm gonna write the function. So if you still remember, the first thing that we're gonna do is the function, right? The function to represent the curve. So I'm gonna do that now. So our function is gonna be a function that will take one input variable. That's the horizontal coordinate. That's the x, and then it's gonna return another floating point number, which is the value of the function. So for testing purposes, we're just gonna use a very simple function. Let's just call it y equals to x squared. We're just gonna For testing purposes, we're just gonna use a very simple function. In reality, the form of the function could be very complicated, right? But for testing purposes, we're just gonna write a very simple function. So we're gonna return a double. We're gonna call our function just for func. The name of the function is just a func, and then the input is gonna be a double x, right? And then we're gonna return x multiply x. So that's gonna be our representation of a very simple function, y equals to x squared. That's our curve, and we need to calculate the area under this curve for a certain finite interval, right? Okay, so we have a function. Now let's try to write our code for. Let's try to write the main function. So int main. And this time for the int main, I'm gonna have two inputs. The first input is called argc, which is the integer, and then the second input is a pointer to a char array. It's called argv. And these two command line inputs, is gonna come from the command line arguments. So it's gonna come from the command line arguments, and argc is gonna be the total number of command line arguments. So that's why it's called argc, right? Arg command line, and then arg count. It's not command line. Arg count. It's basically how many command line arguments we are having to the main function. And then the second input is a CHR star is basically a char pointer, but it's not just a char pointer. It also has this kind of empty square bracket behind the argument, the name of the parameter. That's argv, right? Which means what? It's it's an array of char pointers, right? So it's not just a single char pointer. It's an array of char pointers, right? So the length of the array is going to be the total number of arguments, command arguments, and then the content of those command arguments are going to be pointed to by the char pointer, right? You'll see how we can actually use these two types of command arguments very quickly when we actually try to run this particular computer program. So as before, we are going to sort of do our initialization first. Do our MPI initialization. So the MPI init is going to take the two arguments. We're just going to pass the two arguments over to MPI init, right? And then we're going to have an MPI size. That's the total number of ranks we're going to use in this particular program. So we're still using the COM word communicator. We're going to get the size. MPI rank. Get rank. So we're getting the unique ID for each of the different processes. Here we're going to introduce one more variable. That's the root rank, and we're gonna call it MPI root, and it's gonna have a value of 0. So MPI root is gonna be the root rank from which we're going to broadcast our data, and then we're going to also perform our reduction operation, and then save the results to the root rank, right? And in this particular program, we're going to use rank 0 as the root rank. But you don't have to use rank 0 as the root rank. You can use any of the rank that's the that's inside of your uh, communicator, right? But in practice, the reason that we are using rank 0 as the root is because suppose your MPI size is 1. You have just one rank in your entire calculation. Then MPI rank is going to go from 0 to 0. So you have just one process in your calculation, right? So if you set MPI root to a value that's larger than 0, then you could actually reducing or broadcasting from a non-existent rank, right? So that's why we're actually putting 0 into MPI rank, because even if your MPI size is just 1, you have just one rank in your communicator, root rank 0 still exists. That's the only rank in your process, right? So MPI root will not be sort of a non-existent rank. So that's our MPI root. And then we're going to define a bunch of variables to just represent the data structure we're going to use. Right, n rectangles, the total number of rectangles, domain width, x left, x right, that kind of thing. We're going to define variables for each one of them. So we're going to have a int. We're going to have an integer. That's n rectangles. That's how many rectangles in total we're actually having for the entire domain, right? And then we're going to have a double to store the left boundary of the x of the domain, double for the right boundary of the domain, and then a double for the domain width, which can be computed from the left and right boundary, and then another double for the rectangle width. So a rectangle width is basically just the domain width divided by the total number of rectangles, right? And then we're gonna have another flag variable. We're gonna give it a char. That's the rule we're gonna use for doing the integration. For our first try, we're gonna do just a Riemann sum of rectangles. But in our second try, we're gonna improve our algorithm. We're gonna improve the accuracy of our algorithm by using a trapezoidal rule. So we're gonna try to implement two different kinds of calculations, right? So now let's before we actually do anything, let's call MPI finalize, just in case we forget to finalize the calculation, to close up the calculation. So now let's try to write some code that's going to use the broadcast capability of the message passing interface, right? So what I'm going to do is that I'm going to gather some command arguments from the user, right? When the user actually runs the program, it's going to give the program some command arguments. I'm going to gather those command arguments, and then I'm going to do some calculations to compute all those variables, right? But this kind of gathering process and this kind of calculations for those basic parameters, I'm going to do that just on the root rank. I'm going to do that on MPI root, right? So I have just one rank that's going to do those calculations, right? Once that rank, the root rank, actually obtains the values for those parameters, that root rank is going to broadcast that information to every other rank by using an MPI bcast. So how do I actually make sure that only the root rank actually does the calculation, right? I do a if switch. I do a if MPI rank. So MPI rank is going to be unique, right? It's going to be different for different ranks. So if the MPI rank actually equals to MPI root, so I'm in this particular bracket parentheses, I'm actually comparing the rank from each of the different processes to MPI root, which is basically a constant, that's 0. So I'm actually looking for the correct rank that equals to 0. So if the MPI rank actually equals to 0, then I'm gonna do the following calculations. Otherwise, I'm gonna skip all those calculations. So this way, I actually make sure that only one rank actually does the calculation. So how am I going to do that? So inside this particular if branch, first I'm going to check to see if argc is equal to 5 or not, because I'm actually expecting 5 command arguments from the user. So if it's not equal to 5, so if the command arguments, the total number of command arguments is not equal to 5, I'm going to exit the program right away. I'm going to print out something to the error, to the standard error, incorrect number of command arguments. Give it some exclamation mark, and then I'm going to just do a hard exit 1. Right. So if the command arguments is actually exactly equal to 5, then I'm going to do the rest of the calculations. So n rectangle, the total number of rectangles is going to be the first command arguments. But the first command arguments is supposed to be a char array, right? It's supposed to be a char array. It's a char pointer, basically, a char pointer. It's a pointer to a character array, to character. So how do I actually convert that into an integer? I can use an intrinsic function that's called a to I, right? A to I is basically converting a character array to a integer. So argv, the first. Why do I actually start with 1, right? I was telling you every array in C++ is actually 0 based. So where is the argv0? In fact, argv0 also exists, but argv0 is actually the name of the command that we're actually using. So once we have finished compiling the area.cpp source code, we're going to get a binary that's called area. And then when we actually run that particular program called area, argv0 is going to store the name of the command that we're running, that's area, right? But everything that's following the area command is going to be a command argument that starts with 1. So argv1 is actually going to access the first command argument that's going to follow the name of the command area. So that's why we're using argv1. So that's going to be our first command argument. And then xleft equals to, that's going to be our second command argument. But again, we have to convert it from a character array to a floating point number. And we can use an intrinsic that's called a to f. A to f actually returns a double. So xleft happens to be a double also, so it's okay. So argv2, and then xright equals to a to f argv3, and then rule. Is it going to be just a rectangles, or is it going to be just trapezoids, right? Rule equals to, so argv4. So if we just write like that, it's going to be a pointer to the memory location of a character. It's not really a character, but here we're actually defining rule as a char. So we have to convert a char pointer to a char. So how do we actually do that, right? So we looked at how to, in previous slides, we looked at how to actually convert, a variable. How do we actually convert a variable to its address by prefixing it with the ampersand, right? And here we have just the opposite. We have to convert the address to the value, right? And all we have to do is to prefix it with the star. The star is basically the opposite of the ampersand. This way we can actually get the char value stored in the argv4, right? So here we're gonna do some other error checking. So if the rule is not equal to capital case R, that's for rectangles, and the rule is not equal to T, that's for trapezoid, and rule not equal to small r, right? And for rectangle, rule not equal to small t, okay, small case t. Then we're gonna send out some error message. Incorrect last command line. Argument must be big R, small r, big T, or small t. and then we're just going to do a hard exit. We will not continue to execute. But if it passes this particular error checking guard, we can actually compute the domain width. Domain width equals to x right subtract x left, right? And then rectangle width is going to be the domain width divided by the number of rectangles. So all those variables, all those basic variables now has values. They now have values only on MPI root, that's rank 0, right? Those values are only assigned, all those containers only filled up on rank 0. On every other rank, it doesn't have values yet, right? So on rank 0, all those values, all those containers actually have undefined values. All those containers have undefined values, right? So you have no idea what are the values actually being stored in those containers. So what we need to do now is to broadcast all those data from the 0th rank, from MPI root, to every other rank. And so we need to call the MPI bcast. We need to call the MPI bcast. So how we are going to call that, right? How we are going to call that? So first, let's call comworld.bcast. So the first number we're going to broadcast is the number of rectangles. So we're going to give it. We're going to take the address of n rectangle, and then we have just one input. Basically, we are just looking at this particular. So that's the address of the buffer we are actually sending out, broadcasting, and then how many we're counting. What's the count? And then the data type. It's going to be an integer, and then the root. So the address of n rectangles, right? And then how many numbers we're sending out? It's a count. It's just one, and then it's an MPI int, all capital case, and then MPI root is going to be the root rank we're broadcasting from, right? So that by doing that, by doing this particular command, by doing this particular statement, the n rectangles value that exists on MPI rank are going to be broadcast to every other rank, right? So one common mistake for beginners is to actually put this particular command inside of this if branch, inside of this if branch for MPI rank equals to MPI root, right? If you do that, it means that only rank 0 are going to call this bcast. Every other rank are not going to call this bcast, and you won't get the expected effect. So no other rank are going to actually, because every other rank is not participating in the bcast, they are not going to receive the values, right? The reason they are not participating in this bcast is because you're actually putting this bcast inside of this if branch, right? This if branch actually makes sure that only rank 0, when MPI rank actually equals to 0, it's going to call the bcast, right? No other rank is going to call the bcast. So you have to make sure that this bcast is being called by every rank, not just the root rank. Even though the root rank, the data is going to come from the root rank, but every other rank has to participate in the bcast call, right? You have to make sure that every rank actually calls the bcast in order to actually receive the data from the root, right? So that's for the in rectangles, and let's do the same thing for every other parameters. We're going to have 6 parameters, so we're going to do 6 bcast, right? The first one is in rectangles, right? And then the next one is going to be x left, and then the next one is going to be x right, and then the next one is going to be domain width, and then the next one is going to be rectangle width, and then the next one is going to be the rule flag, and then each one of them is going to have a different type. This one is going to be a double, and then this one is going to be a double too, and then this one is going to be a double, and then this one is going to be a double, and then this one is going to be a char. And we're done with our broadcasting. We're done with our broadcasting. So now we have the total number of ranks over the entire domain, but we don't really know how many ranks, how many rectangles are going to exist on each of the rank. So we need to compute the number of rectangles on each of the rank. So what are we going to do? We're going to define a new variable that's called n rectangle local. So n rectangle local is going to store the number of rectangles on each rank. So it's supposed to be a subset of the total number of rectangles, right? So how do we actually make sure that the total number of ranks, the number of ranks on each of the rank is about the same? We just do a division. We're gonna just do a division for now. We're just gonna do a division. That's just an n rectangle divided by MPI size. So don't forget, n rectangle now has value on every different rank now because you have done the broadcasting. So every rank is going to have the value, correct value for the total number of rectangles over the entire domain, right? And then you divide by MPI size. That's the total number of ranks in this particular calculation. You are dividing it. So it's two integers dividing each other. So the result is still going to be an integer, right? That's the integer division. It's different from a floating point division. It's an integer division. So this is the integer. This is another integer. You're dividing two integers. You're going to get another integer. And you are leaving out a remainder, basically. So if you divide 10 by 5, then you're going to get 2 rectangles on each of the rank, right? But if you are actually dividing 11 by 5, then you're going to have a remainder of 1, right? But the division is still going to give you 2. So 11 divided by 5 is going to give you a 2, right? But you are leaving out one rectangle. That one rectangle is the remainder. So you need to actually compute the area for the remainder also, right? So for the remaining rectangles also. So how we are going to handle this remainder issue, right? We're going to keep all the remaining rectangles on the last rank, right? How do we actually do that? So I'm going to compare my rank. So MPI rank. I'm going to compare it with MPI size, subtract 1. So if I actually have 5 different ranks, 5 different processes, then the last rank is going to have a rank of 4, right? Because rank starts from 0. So 0, 1, 2, 3, 4. The last one is going to be a 4, right? The last one. So if MPI rank, if my rank actually equals to 4, then I'm going to catch all the remaining rectangles by just doing a n rectangle local plus equals to n rectangle modulo MPI size. So n rectangles is the total number of rectangles. Modulo MPI size is going to give me the remainder of the division. So if there's 11 rectangles and MPI size is 5, then this modulo is going to give me 1. That's the remainder. So 11 divided by 5 equals to 2, and then with the remainder, that's 1, right? And then the modulo is going to give me the remainder. So this calculation is going to give me 1. And then plus equals 2 is equivalent to this thing. Is equivalent to plus this. So basically, I'm adding n rectangle local with the remainder, right? That's the existing value of n rectangle local plus 1. So the current value is from what? The current value is from this division. So 11 divided by 5, that's 2, right? 2 plus 1, that's 3. And then I'm assigning the result back to n rectangle local I'm assigning 3 back to n rectangle local. And this kind of a reassignment only happens for the last rank in my communicator. That's rank 4, right? So I'm going to go back to plus equal. So the last rank is going to do some more calculations than the rest of the ranks, right? Because it has to catch the remainder of the division. So now we have a good idea about how many rectangles has to be handled on each of the different ranks, right? And then we have to get another variable. We have to get another variable. Suppose we're actually partitioning all those rectangles onto different ranks. Then what's going to be the left boundary? What's going to be the left boundary of the leftmost rectangle on each of the different ranks, right? And we can actually compute that without too much of a difficulty. So all we have to do is to introduce another variable. Let's call it x left local, right? That's the variable that's going to store the the left boundary of the leftmost rectangle on each of the rank. So how do we actually compute that? We compute that by using x left, the global left boundary. That's the left boundary of the entire domain, basically x left. And we got every rank now has a value of x left, right? The correct value of x left, because you have done the broadcasting already, right? So that's going to be our starting point. We're going to multiply. We're going to add rectangle with multiply MPI rank multiply n rectangles divided by MPI size. So how do I actually get this particular formula, right? X left, that's the left boundary of the entire domain, right? That's the entire domain. That's our referencing point. That's our referencing point. So for rank 0, that's going to be the left boundary, right? For rank 0, the x left local is going to be equal to x left, right? Let's see if that's true. So if for rank 0, MPI rank is going to equal to 0, right? So 0 multiplied with everything, that's 0, right? So the entire thing is just a 0 for on rank 0. So x left local equals to x left on rank 0, right? And then on rank 1, if MPI rank actually equals to 1, then the left boundary is going to be x left plus the width of the rectangle, multiplying with what? Multiplying with the total number of rectangles on rank 0, right? Because for rank 1, its leftmost boundary happens to be the rightmost boundary of all the rectangles on rank 0, right? So all you have to do is to count how many rectangles you have on rank 0, right? How many rectangles we are having on rank 0 is given by this particular formula, right? It's n rectangles divided by MPI size. So that's here, n rectangles divided by MPI size. We have this many rectangles on rank 0, right? So all we have to do is to multiply this many rectangles, right, by the MPI rank. For now, we are looking at MPI rank equals to 1, right? And then multiply with the width of the rectangles. Then we get the leftmost boundary on rank 1, right? On rank 2, what's going to happen, right? It's going to be the leftmost boundary on rank 2 is going to be the rightmost boundary on rank 1, right? So the total number of rectangles that's before the rank 2, the leftmost rectangle on the rank 2 is going to be the total number of rectangles on both rank 0 and rank 1, right? How do we actually get that number, right? How do we actually get that number? It's a on each of the on rank 0 and rank 1, the number of rectangles is basically n rectangles divided by MPI size, right? And then we have 2 ranks already, 2 ranks. So MPI rank equals to 2. Then 2 multiply this many, right? 2 multiply this many, because on each of the rank 0 and rank 1, you have this many rectangles. Just multiply them together. Just multiply by 2, you get total number of rectangles before rank 2, right? And then multiply the width again, and then add x left. So that's how I actually compute the left boundary on each of the rank, right? So before we actually continue our calculation, let's do some printout. let's do some sort of intermediate printout. MPI rank, just to make sure that so far we are actually doing the right thing. Rectangles local and rectangles local, and then x left local, x left local, ENDL, right? And then let's go back to our shell to compile it. C++ std equals to C++ 14 and then dash O area dot cpp. So it looks like I have some compiler errors. So one of the things is called n rectangle was not declared in this particular scope n rectangle. So it's called n rectangles, but here I'm actually using n rectangle. So I missed an S, right? And then what else? I may have made the same mistake here. So I have an S here, right? And then in rectangles, looks like I corrected that error. And then error domain was not declared in this. It's a domain. It's not the spelling errors. Domain. Oh, domain was divided by n rectangles, right? And then what else? And rectangles local. And rectangles local was not declared. And rectangles local. I missed an S here. And rectangles local. So that should correct all the different mistakes. Let me compile it again. Oh, and rectangles. Missed another S. Rectangles local. Okay, so now it looks like it's passed the compiler. So let's try to run it. I'm gonna use 8 processes dot area, right? So it's actually expecting 5 command line arguments. So the first command line arguments is gonna be the total number of rectangles. Let's just give it like a 1000 or something. And then the next one is the left boundary. Let's give it like 1, and then the right boundary 10, and then the next, let's just call it R, rectangles, right? So it's gonna give me this kind of printout. So rank 0 gonna have like 125 rectangles, right? Because I have like 8 different different ranks. So MPI size is gonna be 8, so it's just gonna do an even division. 1000 rectangles are gonna be divided evenly on those 8 processes. So each one is gonna get 125 rectangles, right? But suppose I do this call, but with not 1000 but 1500 rectangles from 1 to 10 with R, then it's gonna give me a different distribution, right? So rank 0 to rank 6 is gonna be 187, right? And then the last rank, that's rank 7, is gonna have 191 rectangles. It's gonna have more rectangles than the rest of the ranks. And then each rank is gonna have a different left starting point. So for rank 0, it's gonna start with the left boundary of the domain, that's 1, which is exactly the same here. And then the last rank is gonna have a left boundary that's 8.854, right? Because it's the boundary of the right domain is 10. It's supposed to be larger than 8.854, right? So it looks like so far we have done pretty well. have computed everything correctly, right? So now let's keep working on it. Let's keep working on it. Um, Once we have all those variables, we can start to actually do some local summation, just to compute the summation of the area for each of the uh, within each of the rank, right? So all we have to do is to define another variable and then initialize it. Let's call it sum local. Sum local, we're going to initialize it to 0.0d double. It's going to be a double precision number, right? So for now, let's just work on the rectangular summations. So if rule equal to, we're comparing it with R rectangles, or rule equal to small r, then we're going to just use rectangles, right? And later on, else if rule equal to t, or rule equal to small t. Later on, we're going to write the code for the trapezoidal rule. Right. For now, let's just work on the rectangles. So if we have this many rectangles, if we have this many n rectangles local, this many rectangles on each of the rank, all we have to do is to compute the area for this many uh, rectangles on each of the rank, on each of the core. So we don't really have to compute n rectangles. We just need to compute n rectangles local, right? And we can easily do that within a loop, So we're going to do a for loop int I rectangle. That's going to be the iterator. That's going to be the index of the rectangles on each of the rank, which is going to go from 0 to I rectangle smaller than n rectangles local, and then plus I rectangle, right? We're going to iterate through this many rectangles, and then within each of the iteration, we're going to compute the area. So how do we actually compute the area? The first thing we're going to do is to get, so if we actually go back to this particular figure, so for each of the rectangle, we're going to try to, for example, if we are looking at this particular rectangle, right, we will need to get its left boundary, right? Its left boundary. And then from this left boundary, we're going to compute the value of the function, which is basically the height of the rectangle. So I need two variables. One is the left boundary of this particular rectangle, and then I need the height. I need to get the height of the rectangle by calling the function. So how do I actually get the x boundary, the left boundary of the rectangle, right? So let me define another variable. Let's call it my left. My left is going to equal to what? It's going to equal to x left local. That's the leftmost boundary for all the rectangles on the current rank, right? And then that's going to be my reference point, right? I'm going to add, that's the, so I rectangle is going to be the index of the current rectangle that's inside of this particular loop, right? And then multiply with rectangle width. And this way I can get the left boundary, the location of the left boundary of the current rectangle, which has an index of I rectangle on my current rank, right? Once I have the left boundary, I can use the function to get the height, right? So auto my height equals to func my left, right? This way I get and then the area is just the rectangle width multiply with my height. So then that's the area of the rectangle, right? That's the area of the rectangle. So all we have to do is to accumulate this particular area to local sum. So sum local plus equal to, and then this way we actually get access. We get our local sum, right? We got our local sum. So this is a rectangular rule. And then we're gonna work on trapezoidal rule later on, right? But now let's let's try to finish all the calculations that's related to rectangular rule, right? So now we have a local sum. That's a summation of the areas on each of the ranks. Now we have to collect all those local sums together into a global sum, right? And we're going to use a MPI reduction operation to do that. We're going to use a MPI reduction operation to do that. So how are we going to do that? How are we going to do that? First thing we're going to do is to define another sum. That's going to be the global sum. We're going to initialize the 0, 0, d to a double, right? And then I'm going to call the MPI reduce, MPI COMMWORLD. I'm going to call reduce. So if you do not remember how to use the reduce function, just take a look at the user manual, right? The reduce function, it's expecting a value that's the send buffer, and then the value for the collection buffer, right? And then the result buffer, the count, the type, the operation, and then the root rank, right? So we're gonna follow this particular syntax. So the first input is gonna be the send buffer, which is the address of the local sum local. And then the second input is going to be the address of the receiver buffer. That's the reduction result, which is supposed to be the location of the sum. And then it follows the count, how many. We have just one number, right? And then followed by the type, MPI double. And then followed by the operation we want to do that, which is sum. And then MPI root, right? That's the root where we want to collect all the results to. And then we are done. We're done. All we have to do is to print out. This particular global sum. But this global sum has the correct value only on the root process, only on the root rank. So if we want to print out the result, we can only actually print out the correct result from the root rank, because the local sums are being reduced to some variable that exists only on the root rank, right? So now let's if MPI rank equal to MPI root, then we're gonna print out the result. So we're gonna just do a cout area on the curve, right? And I'm just gonna print out sum, and that's it, right? So for this particular simple example, for this particular very simple curve y equals to x squared, we can actually compute the integral analytically. We can actually get an analytic integration of this particular curve, right? So if we just do an analytic integration, it's going to be x cubed divided by 3, right? So we can actually get the exact solution. So let's just define an exact solution. The exact solution is going to be x right times x times, it's going to be the cube of x right subtract the cube of x left and then divided by 3.0. That's going to be the exact result, right? So let's also print out the exact result. And then we're going to print out the difference. We're going to print out the difference in terms of percentage. So we're going to use FABS to take the absolute value of the difference, exact, subtract sum, and then we're going to divide it by exact. So that's going to be our printout as our results, right? So let's give it a try. I'm gonna comment out the previous printout. I'm gonna comment out this line. So I have just one printout for the entire program. That's the result. So let me go back to recompile it. and then let's rerun it. So area on the curve is 332.7, and then the exact value is 333, and then you have a difference. So this is not in terms of percentage. If I want to get the percentage, I have to multiply this division by 100, and then we're going to print out a percent sign, and then in the end of line. So the difference is quite small, just 0.089 percentage, right? And this difference is going to be even smaller if we actually increase the total number of rectangles. So MPI run MP8 area. Suppose we increase it to like 10,000, right? And then from 1 to 10, and then R, right? So 3 that's a much smaller difference, right? That's a much smaller difference, right? And if we want to make it even more accurate, we can just keep increasing our uh, rectangle number, right? This way it's becoming even smaller, right? And that's by using the rectangle rule. But suppose we want to use the trapezoidal rule. So how do we actually use the trapezoidal rule? So let's go back to this particular figure. Here we're actually using the area of a rectangle to approximate the area underneath the curve, right? The bad thing about rectangle is that it's got a flat top. So the top doesn't have a variable value. It's just a flat. It's just a constant, right? For every rectangle, it's just like that. But we know the curve itself actually has a variable sort of height for a particular segment, right? So a better approximation could be obtained by making the top of the rectangle sort of following a linear trend, right? So suppose we actually connect the two dots here from here, right? So we are not getting a rectangle anymore. We are getting a trapezoid, right? So if we actually connect these two dots, we're getting a trapezoid, right? So if we can actually do this thing for every point, then we are getting lots of trapezoids instead of rectangles. So a better approximation, for example, if you look at the last rectangle, if we actually connect this point with this point, we're getting a trapezoid. So a better approximation could be obtained by just changing all the rectangles to trapezoids, right? So how do we actually compute the area of trapezoids, right? It's not that difficult, basically. So the formula for computing the area of trapezoids is basically the average of the two bases of the trapezoid multiply the height of the trapezoid. So what's going to be the basis of our trapezoid, right? The two bases of our trapezoids are going to be the two vertical lines. So it's going to be this line, and then it's going to be this line. That's going to be our basis of the trapezoid, right? And we can actually get the two bases by just using the functions, by just using the function values. So the height of this basis is the value of the function at this particular point, right? And then the height of this particular basis of the base of the trapezoid is just the height of the function at this particular location, right? And then the height of the trapezoid is basically the width of the rectangle, right? That's the height of the trapezoid. So a simple change of the from rectangles to trapezoid could actually potentially increase the accuracy of our approximation quite dramatically. So now let's try to implement our trapezoid rule. So in order to actually implement the trapezoid rule, we're going to need a vector to store all the different heights. So for rectangles, the total number of heights we're going to need is basically just the same. It's the same as the total number of rectangles, right? because the rectangle for rectangles the two sides have identical height, right? So this height is the same as this height, right? But for trapezoids, it's gonna be more. So every trapezoid is gonna have like two bases, right? It's gonna have two heights. It's gonna have two heights, but it's still okay because we don't really have to double the vector for storing the heights uh, because uh, because you can sort of see the base, the bottom base. If we just examine this particular trapezoid, right? The bottom base for this particular trapezoid is this particular height, right? And this particular height is actually exactly the same as the top base of a trapezoid, uh, of this particular trapezoid, right? So the length of the vector for storing all the heights of the different trapezoids is just going to be the total number of trapezoids plus 1, right? Because you have duplicates. The base of the previous trapezoid is the bottom base of the previous trapezoid is the top base of the next trapezoid, right? So all we need is basically just a vector to store the heights. So what's going to be the length of the vector? What's going to be the length of the vector? The length of that vector is basically n rectangles plus 1, right? So we're going to define a vector. It's going to be a vector of doubles, right? We're going to call it heights. And then we're going to use the constructor to initialize this particular vector. And how many heights we're going to need? We're going to need n rectangles local plus 1. And then we're going to initialize every height to 0 first, right? And then we're going to loop through all the different locations and then try to fill up the heights vector. So for I rectangle equals to 0, I shouldn't actually call it I rectangle anymore. I should call it I trapezoid, right? But it doesn't really matter too much. So n rectangles local plus 1, and then plus I rectangle. So auto, my left is going to equal to x left plus x left local plus I rectangle multiply rectangle width, right? And then heights I rectangle is just going to equal to func my left, right? So if you actually look at the difference between this particular loop and then this particular loop when we're actually computing the area for each of the rectangles, the only thing that's different is actually the range. We have to actually compute one more. We have to compute one more. The reason is because when we're doing rectangles, when we get to the last rectangle, all we have to do is to compute the height of the left boundary, right? But when we are doing trapezoids, we have to compute not just this side, we also have to compute this side, right? And this side actually belongs to the rectangle of the next one. That's outside of the boundary, but still we need to compute the height of this side, right? So that's why we have to sort of do like one more rectangles, right? To do one more, to do just the one over the rectangles. Once I have the heights, I can compute the area of the trapezoids quite easily. All I have to do is to do another loop. I rectangle equals to 0, I rectangle smaller than. But this time it's going to be n rectangles local because that's the total number of not the basis of the rectangles, but it's actually it's not the basis anymore. It's actually the total number of trapezoids, and the total number of trapezoids is actually identical to the total number of rectangles. So that's n rectangles local. It's not plus 1 anymore. And then plus I rectangle. And then all I have to do is to compute the area, right? So auto, my area equals to, so heights I rectangle plus heights I rectangle plus 1. So that's the left base of the trapezoid. That's the right base of the trapezoid, right? And then I have to get the average divided by 2.0 and then multiply with uh, rectangle width. That's my area. That's the area of one trapezoid, right? And then all I have to do is to change some logo. Some logo plus equals to my area, right? And that's it. That's it. That's all I need to do in order to actually change the integration rule from a rectangular rule to a trapezoid rule, right? And then let's go back to recompile it. Looks like I don't have any compiling error, so let's give it a run. But this time I want to test out the trapezoid rule. So again, I'm gonna use how many? 6 nines, right? 6 nines, and then 1 to 10. But this time I'm gonna use T, big T. Okay, so you can sort of see the difference in terms of the error, right? So this was computed using rectangular rule, and this was computed using trapezoidal rule. You can see the difference. The error in the numerical integration is actually much smaller, right? By using the trapezoidal rule. And if you want to try a different want to try a different number of trapezoids, let's just try like 1000, right? 1 to 10. If it's a rectangle, then that's the error, right? That's the error. That's the error. And then if I do the same run, still it's just a 1000 trapezoid, 1 to 10. Change it to T, and then you can sort of see the error is much smaller, much smaller. So trapezoid rule actually gives you a much more accurate results, right? And that's our code. If you want to sort of see the benefit of doing parallel calculations, I would suggest you to use another Linux utility that's called time, right? Time MPI run. If you do a time MPI run, it's going to tell you how long it actually took to actually do the calculation. So here it's actually telling you it took like a 0.114 seconds and 0.208 seconds for the user, right? It's actually giving you a timing information for a particular calculation. So you can try different number of processes. You can change MP from like 1 to 2 and then to 4 and then to 8, and then see how the runtime actually differs for those different kinds of MP values. By changing the MP values, you are basically just changing the total number of processes or total number of ranks or total number of cores you're actually using for this entire calculation. So by increasing MP value, you are increasing the total number of cores used in your calculation. Right? You're gonna see that the time used for the entire calculation is going to reduce as you increase MP if you actually fix every other parameters. If you fix every other input parameter to the program, but just to change MP value, you're going to see the used time being reduced as you increase MP values. Of course, this kind of experiment only makes sense if you actually have a quite large number of rectangles or trapezoids. 1000 is going to be too small for you to actually see the difference, right? But if you actually have like a 1 million or something, you're going to see the difference. You're going to see the difference. Increasing the number of process counts is going to reduce the time quite dramatically, almost in a linear way, right? So if you double the number of processes, you're going to reduce the runtime by like half. So I'm not going to do this particular experiment in this video, but you might want to do that.